Hello everyone, this is Muhammad again, and I am with the last ICP, which is ICP 11 of the course Big Data Analytics. So today we are going to talk about the U network, which is the segmentation of the images by pixel. So let us start from the importing the libraries here, and after importing the libraries. Here, we need to integrate the Kaggle with the Google Colab because the data set on Kaggle is almost 1 GB of size, and it takes very much time to download it. So we are just integrating the Kaggle here, and here I just generate the token, API token from the Kaggle account, which is I'm using the Sayed Shah, my professor. Uh, API token because mine was not working here. Okay, so after here, the kaggle.json, it's a file JSON format which have a username and a key here. So I'm just making here the kaggle folder, and I'm copying that kaggle.json to this folder. After that, I have just changed the permission, and here I'm just displaying the Kaggle dataset list. So it is all the dataset list over here, but we are interested in data science Bowl 2018 datasets. So this is the API to download the dataset here. So I'm just downloading here. Moving ahead, I just make a new folder, train folder. So the reason for creating this train folder is to unzip this dataset into this folder. So here, this command is unzipping the train zip file into the default directory and into the train folder. Okay, moving ahead here. So in this cell, I am just resizing the image, like I'm just resizing all the image with the same dimensions, so which is the weight, height, and channels. So the weight is 128 pixel by height is 128 pixel. The channel is 3 because it's a RGB image. So this function is in that. Okay, so let me come with the modified network. So this is the default network, and here I just modified the network here. So what I did here, so the U network have two parts. So one is contracting part, which is the right side, and one has the expensive part, which is the contracting part is the left side, and the expensive part is the right side. So you can call expensive part as the upsampling of the image to its original dimensions. Okay. So here we have a lot of networks like for C1 to P1, C2 to P3. I just added C31 network layer in the model. The reason is the features get complex. So the first, for example, so here the first layer is extracting the edges of the images, and the second layer, second network is extracting, more features. Okay, the feature getting complex. So to handle those complex feature, I just add the one more layer to extract as much as possible, as much features from the image, to segmentize the image pixel by pixel very accurately and get the best result. So the architecture of U network is symmetric. So the left side should be equal to the right side. So I have added the layer in the contracting part. So I need to add the layer which is transpose layer with convolutional layer, 2D layer. on the expensive part to make it symmetric. So here I just added this layer with the transfer 2D to upsampling the image. Okay, so this is the reason I added two things over here in the model, just modified the model a little bit. The next thing, we have a dice accuracy function, which is calculate the accuracy of the model. And here I'm just compiling my model, and this is a summary of my model. And after a summary, this is okay. Here I'm just storing the checkpoint of my model, and storing and this function basically what it does, it just stops your model if there is no you can say that there is the model is training, and after each iteration there is no difference you can see in loss or in the accuracy. So it is good to stop the model early to waste the time. Suppose you have 100 epoch size and you are waiting for the 100 iteration, like for example if the model have the 76% accuracy, and you are hoping that if the model reach at the 100 epoch, so the my accuracy would reach to 80%, 85%, and in fact in real this not happen. You are just wasting your time. So this function just stop the model. But here I just, you can see that I just commented out that thing to stop the model early stopping, because I found like my model accuracy was increasing by each iteration, but it was stopping it. So I don't want that. I just want my model to reach at desired accuracy, which I was expecting. So I just commented this out. Also, here you can see that I just increased the epoch size to 40 and the best size to 32 from 16 to 32. The reason is I just want to make my training faster by moving the the half size of the training set back and forth. So the accuracy with the default model, what was the accuracy before model? It was 80%, and the validation accuracy was 80%, and the dice accuracy was 81%. But after modifying the model, it is clearly seen that the model accuracy is 89% and dice accuracy is 86%. So there is a huge change, like of almost 9% change in the accuracy of the model. Okay, so this is the accuracy comparison. Let's look at the visualization comparison here. So in visualization comparison, I have made a comparison here. So this is my test image, input image here, and this output is the output with the default model, like without modifying the model. And this output on the right is the output of modified model. So you can see that this image is very clearer than this one, and it is the exact replicate of this image. And there, I mean, some points are missing over here, and it is very dark. And this one is comparing to this one is very clear, and it's predicting each pixel here, each sample here. So this is the clear comparison before modifying the model and after modifying the model. So hope you enjoyed this video, and if you have any question, any comment, any thoughts, just feel free to reach to me, or you can comment on my YouTube video, or you can email me on my email address. And see you then. Thank you.